Hello and welcome back. This is video 3 of Unit 3, and it's going to cover cluster analysis. And once again, this is presented by EDU Onyx. Cluster analysis, very important in industry. This is going to be arguably the most popular or primary application of unsupervised learning. Thus, we are going to spend a video talking about it and how it is implemented. So this is an important video, probably the most important one in this unit on unsupervised learning because it's going to be arguably what you're most likely to use in the future. So pay attention and let's dive right in. So cluster analysis, or also called data segmentation, has a variety of goals, and all of these goals relate to grouping or segmenting a collection of objects into subsets or clusters such that those within each cluster are going to be more closely related to one another than objects assigned to different clusters. So an object can be described by a set of measurements or by its relation to other objects. And cluster analysis is also used to form descriptive statistics to ascertain whether or not the data consists of a set of distinct subgroups, each group representing objects with substantially different properties. So this goal requires an assessment of the degree of difference between the objects assigned to the respective clusters. So here on the right, you see an example of cluster analysis, and this is just simulated data, but it was randomly distributed, and here it is segmented into 3 distinct clusters. So you see our green dots up at the top, then the blue in the middle, and the orange in the bottom. Looking at this data, if it was all just black points, it would be hard to say that there were 3 distinct points, but this is an example of using k-means clustering, where we're actually absolutely able to show mathematically that they can be separated into these distinct groups. So central to all of these goals, or goals of cluster analysis, is the notion of the degree of similarity, or probably more often than not, you're going to hear this referred to as dissimilarity. And this is the dissimilarity between the individual objects being clustered. So a clustering method attempts to group the objects based on the definition of similarity supplied to it. So this can only come from subject matter considerations. So our definition of similarity is going to depend on the data that we're looking at. In video 2, when we did our project, we made sure that we did several data visualization steps before actually applying an algorithm so that we could understand the data that we're looking at. In machine learning, once again, it's very important that you understand your underlying data so that you can pick the most appropriate model, or in this case, the most appropriate measure of similarity. So this situation is somewhat similar to the specification of a loss or a cost function in prediction problems like the ones we talked about in our Unit 2 on supervised learning. So now that we have this definition of similarity out there, we can update our goal of these cluster analysis algorithms, and that goal being to partition the observations into groups so that the pairwise dissimilarities between those assigned to the same cluster tend to be smaller than those in different clusters. So here is our official goal, complete with our application of dissimilarities. So this is what we're looking for in cluster analysis. So let's take a look at a couple of different algorithms that can be used to accomplish this goal. So these are the 3 main types of clustering algorithms. The first one being the combinatorial algorithms. So in these algorithms, we are going to work directly on the observed data with no direct reference to an underlying probability model. So we're not going to assume that the distribution is Gaussian. This would be considered perhaps a non-parametric approach. We talked about that in our intro video, non-parametric versus parametric, where we do assume such distributions such as Gaussian. And this is going to be the opposite of that. No underlying assumptions. We're going to work directly on the observed data. The next one is mixture modeling. So this is going to be the parametric approach in that it supposes that the data is a sample from some population described by a probability density function. So this density function is characterized by a parameterized model taken to be a mixture of component density functions. So each component density describes one of the clusters. This model is then fit to the data by maximizing the likelihood or corresponding Bayesian approaches. So in this approach, we're going to have different clusters, and we're going to assume that each cluster has its own probability distribution, such as a Gaussian distribution or other similar models such as that. And we're going to separate it into distinct clusters where each cluster has that distribution. You don't have to use just Gaussian distributions. One cluster could be a Gaussian, whereas another one could have like a Bernoulli distribution or some other type of distribution. So that's mixture modeling, and our third one is going to be called mode seeking. So mode seekers take a non-parametric perspective, and they attempt to directly estimate distinct modes of the probability density function. So observations closest to each respective mode then define the individual clusters. So we've previously touched on mode hunting or bump hunting, you might hear, and this is the third type of clustering algorithm. And mode seeking, we're not going to touch on it very much, but it does come up, so it's important to know about. We're going to talk exclusively about k-means clustering, and this is because it is by far the most popular combinatorial algorithm, which is by far the most common type of clustering algorithm. So more often than not, you're going to see k-means clustering. So let's go ahead and dive right into that, explain it more fully, look at some of the math behind it, and as well, an example of k-means clustering being used. All right, so here's k-means clustering, and the k-means algorithm is one of the most popular iterative descent clustering methods. It is intended for situations in which all of the variables are of the quantitative type. So we have numerical values, and then the dissimilarity measure is often chosen to be the Euclidean distance. So this example that we're going to look at is going to be a two-dimensional example, so it's very easy for us to use Euclidean distance. However, there might be the case where we have higher dimensions, and then you have to do dimensionality reductions in order to apply Euclidean distance or something like that. In these examples, the k here in k-means clustering is going to refer to the numbers of clusters that we choose, and this is a value that's predefined. So we can pick the number of clusters. We might not know how many clusters there should be, and then we have to do like a guess and check type method where we maybe use a k-means method with a variety of different cluster numbers, and then choose the one which has the best output. So let's keep going and take a look at the actual algorithm. So here is k-means clustering, and so we're going to start with a three-step process. And before this begins, each of these clusters is going to be initialized with random centers. So we're randomly going to pick points throughout our distribution of inputs and define them as our cluster centers so that we have something to start on and iterate on. And then from there, each data point is going to be assigned to the closest cluster center in Euclidean distance, and that's going to be defined as such. So then step 2, each cluster center is going to be updated and is going to be replaced by the coordinate-wise average of all the data points that are closest to it. So this is why it doesn't matter that we start with random weights. And in fact, it's actually beneficial to start with random weights because the k-means clustering algorithm is not guaranteed to find a global minimum. So in fact, when you're using this method, you often want to start with several different random initiation points, there we go, and go from there and see which one finds the best minimum, because again, we're not guaranteed to find the global minimum. And so our last part of this algorithm is just to repeat these steps, finding the closest center and then updating the center average until the assignments do not change and all of the points are into their respective clusters. So let's take look at an example of this because it actually will help clarify how this works much better. So this image is a k-means example, and in the upper left you see our data. This is just a random distribution, randomly generated. All the points are in black, so we have no clusters yet. Step 1, we're going to assign them to random clusters. So that's all interdispersed. For this example, we're picking 3 clusters, and then in our top right example, we randomly initialize our cluster centers. So we have 3 cluster centers. These are placed pretty much exclusively right in the middle with some slight differences. And then we're going to start iterating over this data. So in the bottom left, each data point is assigned to the cluster of the closest center in Euclidean distance. So we have our 3 separate clusters now. You see we have our purple or pink in the bottom, our green and our orange as defined by the closest center. In the middle bottom, we update the location of that cluster center. So now you see it's moved pretty dramatically outwards, and we continue doing that until our assignments between clusters don't change. So if you look at the middle bottom versus the right bottom image here, you'll see that the pink actually loses many of the data points on the right, and those end up being assigned to the green cluster, as well as some of the bottom points in the orange cluster end up being assigned later to our pink or green clusters. So this algorithm iterates over itself until, once again, we find that local minimum. It's important to remember that it's not a global minimum, so actually this process should be repeated using different initial parameters each time so that we can try to search for the best local minimum. It might be that this is the global minimum, but it's important to try to start in different scenarios so that we can check that. And it's also, again, important to start with a different number of clusters. We should probably check 2 clusters because these could probably be better separated into 2 clusters. We can check with 3 or 4, maybe even more clusters. And this is, again, one of the main reasons why it's really important that we understand our underlying data. So we have data subject matter considerations to take into account when we're applying these algorithms. So that is k-means clustering in a nutshell. Here is a quick summary. Cluster analysis attempts to group or segment a collection of objects into subsets or clusters, such that those within each cluster are more closely related to one another than the objects assigned to different clusters. So this is the goal and approach of clustering analysis. And then more specifically, k-means clustering is the most popular combinatorial algorithm for clustering and uses an iterative descent model to cluster quantitative variables using Euclidean distance as the dissimilarity measure. So those are the main takeaways from this video. We're actually going to look at a live coding example of k-means clustering. So that'll be exciting. That'll be the project for this unit. But before that, actually in the next video, we're going to talk about reinforcement learning. So once again, reinforcement learning isn't necessarily unsupervised learning, but it's not big enough to have a unit of its own. So we're going to talk about it here and now. And reinforcement learning is actually one of the most exciting parts of machine learning research today, at least in my opinion. Reinforcement learning is kind of what's assumed when we're talking about things such as artificial intelligence. It's based off psychology and reward systems. But we'll talk about that all in the next video, so that'll be exciting, and keep listening. Thanks.